Welcome to the lesson on direct current. By the end of this lesson, you will be able to define direct current, abbreviated as DC, and describe its characteristics, as well as its role in electric vehicles as the primary form of electrical power. You will compare and contrast the use of DC in early EVs versus modern EVs, highlighting advancements in technology and their impact on performance and efficiency. You will be able to explain the function and importance of battery technology in storing and providing DC power in EVs, considering factors such as energy density, safety, and longevity. You will understand the different levels of BEV charging, including the application of DC fast charging and how they contribute to the convenience and accessibility of recharging BEV batteries. The lesson will also help you describe the use of power electronics in managing DC power within BEV systems, focusing on components such as inverters and DC-DC converters and their role in optimizing efficiency and performance. Finally, you will be able to discuss efficiency and thermal management challenges in DC systems of BEVs and assess the impact of recent advancements in DC technology on BEV design and performance, including advancements in solid-state batteries, power electronics, charging infrastructure, and their implications for the future of electric mobility. First, let us define what we mean by direct current. DC is a type of electrical flow where the charge moves in one direction only. Unlike its counterpart, alternating current, abbreviated as AC, DC does not change direction periodically and flows steadily. This unidirectional flow of electric charge is what makes DC current maintain a constant voltage or current level. It is this consistency that allows for precise control over the power supplied to electronic circuits, which is essential for sensitive electronics that require stable energy inputs. Now, why is DC particularly suitable for energy storage and batteries? Batteries are designed to hold and release energy, and the steadiness of DC makes them ideal for this task. When you charge a battery, you're essentially storing DC energy that can be later used to power devices, from your smartphone to an electric vehicle. Speaking of devices, DC is ideal for electronic devices due to its stable and consistent nature. Devices that require a regulated power supply, like our laptops and handheld gadgets, rely on DC. Inside these devices, even if they are plugged into an AC power source, there's a converter that changes AC to DC to provide a stable stream of energy that the electronics need to function correctly. DC plays an important role in electric vehicles primarily in three aspects: energy storage and discharge, charging, and powering auxiliary vehicle functions. Let us take a closer look at these aspects. Firstly, DC is utilized for storing energy in high-capacity batteries within EVs, allowing for efficient energy storage and discharge during operation. Secondly, DC charging is facilitated either from an AC source via onboard converters or directly from DC fast charging stations, enabling quick and convenient recharging of BEV batteries. DC-DC converters step down the high voltage from the battery to lower voltages, powering various auxiliary vehicle functions such as lighting, infotainment systems, navigation systems, driver assistance systems, and climate control. Presented here is a comparison of DC usage in early electric vehicles, such as the General Motors EV1 model, and modern battery electric vehicles, such as the Tesla Model S. Early EVs had relatively simple power electronics. We will discuss more on power electronics later in this lesson. DC motors were directly powered by batteries, and the systems lacked the complex management and conversion systems found in modern EVs. The batteries used in early EVs were often lead-acid, similar to those used in conventional ICE vehicles for starting, lighting, and ignition. These batteries had lower energy density, were heavier, and had shorter lifespans compared to modern battery technologies. Due to less efficient batteries and motors, early EVs had limited range and lower performance. Charging infrastructure was limited, and charging technology was rudimentary, with most EVs requiring several days to charge fully. The limitations in range, performance, and infrastructure, coupled with the dominance of ICE vehicles, led to lower adoption of early EVs. Modern EVs incorporate sophisticated power electronics, including inverters, converters, and battery management systems. These systems efficiently manage power distribution, conversion, and storage, optimizing vehicle performance and safety. Modern BEVs use lithium-ion batteries and are transitioning to even more advanced technologies like solid-state batteries. These batteries are lighter, have higher energy density, and provide a significantly longer range and lifespan. Advances in motor efficiency and battery technology have vastly improved the range and performance of modern EVs. High-speed operation and acceleration are now comparable to, or even exceed, that of ICE vehicles. Better availability of charging stations and the development of DC fast charging infrastructure have revolutionized modern BEV charging, drastically reducing charging times and improving the convenience of BEV ownership. With improvements in technology, infrastructure, and policy support, modern BEVs are becoming increasingly popular. Now let us take a look at the function and importance of battery technology in storing and providing DC power in BEVs. Batteries serve as a core component of electric vehicles, functioning as a reservoir of energy that powers the vehicle's motor and enables its movement. These batteries store energy in the form of direct current, which is essential for the seamless operation of BEVs. Charging the batteries typically occurs through two primary methods: from the grid and through regenerative braking. When plugged into the grid, the batteries recharge, replenishing the stored energy for continued use. Additionally, regenerative braking harnesses the kinetic energy generated during braking, converting it into electrical energy to further charge the batteries. Battery technologies today boast high energy density, allowing them to store large amounts of electricity within a compact space. This characteristic enables BEVs to achieve longer ranges without compromising on size or weight. Moreover, modern batteries are designed to support rapid charging, ensuring quick and efficient replenishment of energy. This feature significantly reduces downtime for BEV drivers, allowing them to quickly resume their journeys without prolonged waiting periods. Moreover, these batteries readily accept direct current power from fast charging stations, further enhancing the convenience and accessibility of recharging options for BEV owners. A battery management system, abbreviated as BMS, is a critical electronic system in a BEV responsible for managing and controlling the performance and safety of the vehicle's battery pack. The BMS continuously monitors the state of charge of the battery pack, providing real-time information about the remaining energy available for use. This ensures that the driver is aware of the current battery level, enabling informed decisions regarding driving range and charging requirements. By monitoring and controlling the temperature of the battery cells, the BMS prevents overheating during charging or discharging cycles, which can degrade battery life and pose safety risks. The BMS safeguards the battery pack by monitoring voltage levels and preventing the cells from operating beyond safe limits. The BMS oversees individual cells within the battery pack, ensuring that each cell maintains a consistent state of charge. Cell balancing helps to maximize the overall performance and lifespan of the battery pack by preventing overcharging or undercharging of specific cells. The BMS also coordinates regenerative braking, a process where kinetic energy from braking is converted into electrical energy and stored in the battery pack. By optimizing regenerative braking control, the BMS maximizes energy efficiency and increases the overall driving range of battery electric vehicles. Now, let us shift our focus to battery electric vehicle charging. Here, we provide an overview of the three charging types available for BEVs. Level 1 charging, also known as slow charging, is a convenient option for BEV owners who have access to a standard household outlet. By plugging the charger into a typical 110 to 120 volts AC outlet, drivers can slowly replenish their vehicle's battery overnight or during extended periods of parking, such as at home or at the workplace. While Level 1 charging may take several hours or even days to fully charge a BEV, it is suitable for individuals with minimal daily mileage requirements, such as short commutes or local errands. Despite its slower pace compared to other charging options, Level 1 charging provides a practical and accessible solution for many vehicle owners, offering convenience and flexibility for everyday use. Level 2 charging is a step up from Level 1, requiring a 220 to 240 volts AC outlet for operation and professional installation for at-home use. It offers faster charging compared to Level 1, making it a practical choice for BEV owners seeking quicker recharge times. This type of charging is commonly found in various locations, including homes, public parking areas, and workplaces. For instance, a BEV owner who needs to top up their vehicle's battery during a workday can conveniently access Level 2 charging stations installed in the workplace parking lot. Similarly, those residing in homes equipped with Level 2 charging infrastructure can enjoy the convenience of faster charging times, allowing them to quickly replenish their BEV's battery overnight. Overall, Level 2 charging provides a balance between speed and accessibility, catering to the needs of BEV owners in diverse settings. Level 3 charging, also known as DC fast charging, is the fastest option available for BEVs, utilizing DC power to deliver rapid charging capabilities. Unlike Level 1 and Level 2 charging, Level 3 charging bypasses the vehicle's onboard charger, allowing for direct charging. This type of charging is particularly beneficial for long-distance travel, where drivers require quick recharge times to continue their journey. With multiple standards such as CHAdeMO, CCS, and Tesla superchargers, Level 3 charging stations are increasingly widespread, making it easier for owners to access rapid charging facilities. For example, a driver embarking on a road trip can make use of Level 3 charging stations strategically located along their route, allowing them to quickly recharge their BEV and minimize downtime during their travels. Overall, Level 3 charging provides a practical solution for BEV drivers needing fast and efficient charging options, especially when covering long distances. Power electronics in battery electric vehicles consist of various components that manage, convert, and control electrical energy within the vehicle. These components include AC-DC converter, also known as onboard charger or rectifier, DC-DC converter, inverter, battery management system, and regenerative braking controller. We will explore the three main components involved in power electronics in an electric vehicle. The image aims to provide a simplified representation of how AC and DC conversion takes place within a battery electric vehicle. The onboard charger is an essential component that allows the BEV to be charged from an external power source, such as a charging station or a household outlet. It converts the AC from the power source into DC to charge the battery pack. It also regulates the charging rate, ensuring the safety and efficiency of the charge. The DC-DC converter is responsible for converting the high-voltage DC from the battery pack to lower voltages suitable for various auxiliary systems and components, such as the low-voltage battery, lighting, and electronics. The inverter converts the direct current from the high-voltage battery pack into alternating current to drive the electric motors. It also controls the speed and torque of the motor by adjusting the frequency and voltage of the AC output. While regenerative braking, the motor acts as a generator and charges the battery pack via the inverter, which converts alternating current from the motor into direct current. Now, let us shift focus to the two main challenges within the DC system that impact the overall efficiency and performance of electric vehicles. One significant obstacle lies in efficiency challenges, originating from energy conversion losses arising mainly due to charging, discharging, and motor operation. For instance, when a BEV is charged, some of the energy used for charging is lost as heat energy during the conversion from AC to DC power. This reduces overall efficiency. Additionally, battery efficiency is a concern influenced by factors such as state of charge, battery age, and temperature. For example, in either cold or hot climates, batteries may experience reduced efficiency due to decreased chemical reactions, affecting the vehicle's range. Moreover, auxiliary load demand poses another challenge, with additional components drawing power from the battery, further impacting efficiency. Continuing with challenges within the DC system of electric vehicles, thermal management poses another significant hurdle affecting both power electronics and battery performance. Frequent use of cooling and heating systems to maintain optimal battery temperature consumes significant energy, directly reducing the vehicle's range, a critical factor for BEV adoption. This issue is aggravated in extreme weather conditions, where very hot or cold environments place additional strain on the thermal management system, requiring more energy to regulate temperature. Moreover, repeated exposure to high temperatures, whether from environmental factors or rapid charging, can accelerate battery aging, diminishing capacity and performance over time. Most critically, inadequate thermal management can lead to overheating, which not only degrades battery life but also poses serious safety risks, potentially resulting in thermal runaway and fire hazards. We will now explore some of the future advancements in DC technology. The development of solid-state batteries represents a significant leap forward in energy storage technology. These batteries feature solid electrolytes instead of traditional liquid or gel electrolytes, offering several notable improvements. With higher energy density, solid-state batteries can store more energy within a smaller footprint, improving the range and performance of electric vehicles while reducing weight and size constraints. Moreover, they boast improved safety and lifespan compared to conventional lithium-ion batteries, as solid electrolytes are less prone to leakage, overheating, and thermal runaway. Solid-state batteries enable faster charging capabilities, addressing one of the primary concerns of drivers regarding charging times. They exhibit temperature resilience, maintaining performance even in extreme temperature conditions. Other recent advancements, such as improved power electronics, including inverters and DC-DC converters, have seen notable upgrades in efficiency, performance, and size reduction, thanks to the integration of advanced semiconductor materials enabling higher power density and faster switching speeds. Concurrently, advanced thermal management systems have emerged, featuring more efficient cooling mechanisms for power electronics and batteries, such as liquid cooling or active thermal management techniques, alongside optimal temperature control to increase battery performance and lifespan. Complementing these advancements is the development of high-efficiency charging infrastructure, characterized by ultra-fast DC charging stations with increased power outputs, and the implementation of advanced charging protocols for better compatibility and interoperability. Integration of smart grid technologies further optimizes energy management and grid stability, collectively driving forward the adoption and sustainability of electric mobility. The recent advancements in DC technology for battery electric vehicles have had a profound impact on the automotive industry, accelerating the transition to electric mobility. With innovations like improved power electronics and high-efficiency charging infrastructure, BEVs are becoming more accessible and practical for consumers. For example, the development of ultra-fast DC charging stations allows BEV drivers to recharge their vehicles quickly, making long-distance travel more feasible and convenient. Furthermore, these advancements offer more efficient, safer, and longer-lasting energy storage solutions, improving the overall performance and reliability of BEV batteries. This not only addresses consumer concerns about range anxiety, but also contributes to reduced emissions and environmental sustainability. As BEV technology continues to evolve, driving innovation and competitiveness in the market, it reinforces the momentum toward a cleaner and greener transportation future. Let us now summarize what we have learned in this lesson. Direct current is a type of electrical current characterized by its unidirectional flow and constant voltage or current level. In battery electric vehicles, DC plays an important role in energy storage through advanced lithium-ion batteries, charging via Level 1, Level 2, and DC fast charging methods, and powering auxiliary vehicle functions. Power electronics in BEVs manage and convert electrical energy, including AC-DC converters, DC-DC converters, and inverters. However, DC systems in BEVs face challenges such as efficiency losses and thermal management issues. Recent advancements in solid-state batteries, improved power electronics, and high-efficiency charging infrastructure are driving innovation and widespread adoption of BEVs. Thank you.